Okay, I think that we can start the session with this new work, whose title is On Crack Path in Micropolar Continuum and presents Meral Tuna. Okay.
Thank you for the introduction and thank you for your participation to this session. So in this presentation, I will talk about how to find the direction of crack propagation in micropolar continuum. But before starting, I would like to acknowledge the contribution of Professor Trovalusci and Professor Nicolas Fantuzzi. So the presentation consists of 5 main parts. First, I will mention the scope of the work. Then I will continue to talk about the methodologies that we use to find the direction of crack propagation. Afterwards, I will continue with the parametric study that we use to obtain and interpret the results of propagation angles, considering different level of non-localities and mixedity ratios. Finally, I will show the difference between crack paths in classical and non-classical continuum. And lastly, I will finalize my presentation with concluding remarks and possible future works that can be done. So the scope of this work is, with using extended FEM and linear elastic vector mechanics, find the direction in which the crack will propagate in a size-dependent structure. So size dependency occurs when the dimensions of internal structure becomes comparable with the overall length. As you can see, this can happen in any level, and in this case, it is suggested to use non-classical theories to model the mechanical behavior. And we use as one of them micropolar theory of elasticity. This theory is especially used when the structure, the material, is affected by the heterogeneous and discontinuous nature of the underlying material organization. And this is also the heterogeneity and discontinuity also makes structure more prone to fracture type failure. So here you can see different examples with this kind of internal structures, and all of them, the gross mechanical model of all of them are models using micropolar theory. So micropolar theory has a new degree of freedom, which is microrotation. Of course, it's changed field equations, but also here we have 2 new material parameters, besides the classical constant that we know from Cauchy continuum. These are coupling number and characteristic length. So changing the value of these parameters, we can either amplify the non-locality of the system, or we can make the continuum approach to the classical one. As for the fracture characteristics, there are very many approaches, as you know. In this study, we use linear elastic fracture mechanics. And of course, this technique also is very well known by this community. But what is new for micropolar continuum is, because of the existence of microrotations, now we also have couple stress intensity factors. And also, as a new thing, the intensity factors, all the intensity factors are also dependent on the material, micropolar material parameters. And also what is interesting is, as the non-locality of the structure is increased, the deformability and energy release rate decreases, which means that you need to apply more load to initiate the crack propagation. And these are all known facts in the literature. What we propose is, we extended maximum energy release rate criterion to micropolar continuum. This criterion is initially proposed in 70s for classical materials, and it suggests that crack propagates along the direction that maximizes the energy release rate, which is a function of intensity factors at the infinity small branch. There are 2 ways of finding this. First is the well-known one, obtaining the formulation for propagation angle, either without any simplification or considering continuation assumption. Because the first one is mathematically very challenging, here we derive the formulation under continuation assumption. Also, as you can see, also for Cauchy continuum, the 95% of studies use the simplified formulation because it is easy to make any changes. Another way of finding it, which is new, is obtaining the energy release rate manually. So with changing the orientation of infinitesimal branch and obtaining energy release rate for each case, when we have enough data, we can directly find where the maximum energy release rate is, and the corresponding orientation, of course, gives the propagation angle. And this is called second approach, because second approach gives actually very close results to the actual formulation. We use this approach to control our results from the first approach. In any case, we need to find intensity factors, either at the main crack tip or infinitesimal branch. And to do this, we generalize extended FEM method to micropolar continuum, considering also the effect of micro-rotations. I'm not going to give too much detail, but as you know, it is computationally efficient model because there is no need to have conforming mesh with correct geometry, and all the singularity and discontinuity is accounted for through additional degree of freedom at the enriched nodes. And with this method, using interaction integral, we extract the intensity factors, the required intensity factors. Now, we covered the methodology. We can continue with the parametric study. For this, we considered a square plate with an edge crack that is fixed from the bottom edge. And with changing material parameters and prescribed displacements, we covered different level of non-locality and also mixity ratios. But before talking about micropolar continuum, I want to show the results for classical Cauchy continuum, which is already known. I just want to show the difference between approaches. So with actual formulation, the variation of propagation angle with mixity ratio is like this. With simplified formulation, which is the most frequently used one, we have slightly lower propagation angles with a maximum error of 8%. And with this new approach, we can obtain results very close to the actual formulation. Now, we will do the same thing for micropolar continuum. As you can see, in the formulation, we need to find the values of intensity factors, and also there is critical distance. Finding intensity factors is easy. With extended FEM, we can find their values. But critical distance should be predefined. And at this point, for micropolar continuum, we don't know what its value should be. That is why, as the first step, I will exclude critical distance term. So you can see, as non-locality is increased, especially for shear mode dominated cases, the trend of curve changes very significantly. For mode 1 case, we always have self-similar crack growth, which is in accordance with literature. These are the studies that use phase field approach and combined ferrodynamics approach. For mode 2 case, as the non-locality is increased, the propagation angle decreases, which means that the branch approaches to the horizontal line. This also seems to be in agreement with the literature. Now, if we include the contribution of critical distance, you can see that with increased non-locality, and also, with increased non-locality, the angles change. In fact, when we include the contribution of critical distance, we find very close propagation angles with the available literature that's based on a different approach, of course. As for mixed mode case, again, non-locality increases, the importance of critical distance increases, especially for mode 2 dominated cases, which means lower mixity ratio. Now, for the second approach, I already explained this, but in this approach, with proper manipulation of boundary conditions, we can zoom in at the crack tip and magnify it, so the infinitesimal branch can be modeled as a finite small branch, which allows us to numerically model it. Again, we obtain enough data. We have the variation curve that we pick the maximum, we pick the angle that gives the maximum energy release rate. Now, let's see the comparison between two approaches. Up to a certain point, let's say mixedity ratio of 15, the trend seems okay. But after that, there is a strange behavior. Because as you can see from here, we have a certain difference. Then with increased non-locality, this difference between approaches increases, and then it suddenly becomes zero. At first, it makes no sense. But when we perform more simulations for this most critical and strange case with many other coupling numbers, we see that there is actually an offset error between these two kinds of approaches, which means that we can actually, for this critical case, mode 2 dominated cases, offer a correction factor to reduce the difference between approaches. Now, since we understand how to obtain propagation angles, it is time for see the variation of crack paths. For this, I considered 3 different mixedity ratios that does not need any correction, or the critical distance have lower effect. And these are different discretizations that we study to make sure that the resulting crack paths are independent of the discretization. And these are the results we obtained. The black ones is the Cauchy continuum. Here you can see. And the colored ones are micropolar continuum with different level of non-locality. Here you can see the color code. So we can say that for shear mode dominated cases, initially shear mode dominated cases, the crack paths are very different, while for mode 1 dominated case, they sort of converge. But this shouldn't mean that, okay, when the case is mode 1 dominated, we don't have too much difference between crack trajectory. Because in another case study, which is a bending beam subjected to a point load, this is mode 1 dominated case, but also in this case, because there is bending and bending affect couple stresses, you can see that again, we have very different crack trajectory between Cauchy and micropolar continuum. So in overall, the most important thing is, if a structure is size dependent, highly size dependent, we need to use proper continuum theory and fracture criterion, because we have different results. And the things we should do is offering the correction factor for critical cases. Of course, determining the value of critical distance, finding a way to determine its value. And finally, we should compare our results with experimental observations to see if the correct trajectory aligns. These are the references I used, and thank you for your attention.